This is problem 6.79, it's on page 343. The hydraulic cylinder CF, which partially controls the position of rod DE, has been locked in the position shown. Okay. Knowing that the angle theta is 60 degrees, determine A, the force P, which the tension in link AB is 410 newtons, and B, the corresponding force exerted on member BCD at point C. All right, so let's sketch the system. See what we have to deal with here. There's a ground pivot at A, and the link in question, AB, is connected to that ground pivot. There's a vertical height of 200 millimeters. That's not the length of AB. There's a horizontal offset of 45 millimeters. So we can figure out the length of AB. We'll probably have to do that before it's all said and done. There's a cross member, something like this, supported at C by what they said is a locked hydraulic cylinder. Really, that's the symbol for a dash pot, but anyway, I'll draw it like this, I guess. So here's point F. To see. So I suppose that this just acts as a fixed point that can't move. There's a 100 millimeter spacing between B and C and a 175 millimeter spacing on out to the end at D along ACD. And then there's, let's see, let me move point D over here. And there's a member coming off this way. We really don't care about it. Force P basically has an angle with horizontal of theta equals 60 degrees. And what we'd like to know, so I don't forget it, is the force in link AB. And what else? The corresponding force exerted on member BCD at C. So basically CX, CY. What we'd like to know. Okay. Now, like I said, the way to start a problem like this is to take a free body diagram of the overall. In other words, get all the reactions if you can. Sometimes that's doable, sometimes it's not, it just depends. To me, it looks like point C is basically a ground pivot. Let's see if that makes sense. If that's a ground pivot, yeah, that would work. We'd still have basically two members back to ground, so it's not going to move, which is what we would expect, right? Be like a truss, essentially. Except we don't just have two force members. AB will be a two force member. How do I know? Because there's just 2 points where force can be applied. So AB is certainly a two force member, but ACD is not a two force member. Okay? All right. So let's see. I said I was going to get the ground reactions, but I'm not sure that I can. Oh, did they tell us the magnitude of load P?
Hey, we have the magnitude of AB.
AB is 400.
Oh,
410.
did I read the wrong section?
Like,
Yeah, I read the wrong problem description,
you
didn't
get
I?
the right
I'm
angle,
sorry.
but it's the wrong.
Yeah, so AB, we know the force in AB. Force in AB is 410. I think I read the next problem, which I gave you guys as
Read
homework.
680.
Yeah, I read
You can do
680.
that one too.
You can do that one too. So we'd like to know the force P. Well, I basically am. It's just the forward solution. You guys will do the reverse solution. And what else? The corresponding force exerted on member BCD at C. Yeah, so that's the same. All right, sorry about that. Just read the wrong problem. Okay. That's actually not all that difficult. You picked an easy problem for me. You should have had me do the other one. Oh well.
Oh, now everybody's gonna get upset.
All right, so basically we know the force in AB. I think the only insight you would need for this is the fact that the force is directed along the member, that it's a two force member. Because then basically all you need is a free body diagram of BCD. Something like this. There must be some rise information, isn't there? Yeah, there's a 20-degree angle with horizontal. And so, let's just extend that out a bit. D is here, C is here, and B is here. So basically we know that we've got a force of 410 newtons. Our question is, what is the force at P? Pretty straightforward. Looks like there's going to be a little bit of geometry involved, but it shouldn't be too bad because we know that the geometry triangle that defines the direction of this force is basically, let me just put the geometry triangle on top of it in another color, is basically just this triangle, where we have a 45 millimeter side there and a 200 millimeter side there. I'm going to need the hypotenuse length, so someone take 200 squared plus 45 squared and take the square root. So it would give me the hypotenuse length along AB.
205 even.
205 even, all right. I found another triangle today. What was the one earlier?
17, 15, 12,
12, yeah, something like that.
Was it 8?
I think it was 8 actually. Yeah,
Yeah.
that was in, I didn't know there was somebody that came out so nice around. Anyway, there we go. Learn something new every day. Now, I think what I'm gonna do is just set up a simple XY coordinate system. It may be advantageous, it may make it simpler to orient the coordinate system along BCD. I don't know, I doubt it. It doesn't really matter. But basically, what I would say is that the sum of the moments have to be equal to 0. That's probably the easiest way to analyze it. Now, would I sum moments about B, C, or D? C, definitely. Right? Because if I sum moments about C, that'll put P and this known force into my equation, and that's all I need, right? So, summing moments about point C taken counterclockwise as positive, you might look at this and say, well, this is going to be a pain, because if you oriented your coordinate system, well, then all you'd need is this component of P and that component of the 410, right? You can do that. You don't have to. You can think of it as more like a cross product, where you say, well, if I'm summing moments about C, notice that P has a positive X component and negative Y component, right? So what I would say is that P in the X direction about C is going to cause a negative moment. So minus PX times, and let me call, see that triangle? Let me call the moment arm that the horizontal component of P has, let me call it this distance CDY. See what I'm doing? If you see what I'm doing, then you know that I'm going to take the vertical component PY, note that it also causes a negative moment, and multiply it by what distance? Remember, this is point C.
The 175?
CDY. CDX. Notice I'm trying to push the geometry off until later. I'll deal with the geometry later. I want to make sure the statics is set up correctly first. Okay. What about the force at B? Well, yeah, it may be a known force, but I'm going to approach it the same way. The vertical component of this 410 Newton load will certainly cause a positive moment. So I'm going to write plus, and I hate to write it this way, but let's say, well, I won't write it that way. I was going to write 410y, but instead I'll write FAB, or in fact, let me just call it AB. We'll just shorten it. So the force end member AB, I'll just call it ABY. That might be a little bit confusing because, I'm sorry, let me change my mind again. FABY, I think that's going to be clearer because I'm using AB or something like it as a length. Let's stick with that. So FAB, make it clear that's a Y. FABY has a moment arm of CBX. You see that? All I'm doing is taking perpendicular distances to the force components. That's all I'm doing. So BC or CB, it doesn't really matter. I'll call it CBX. See how I'm pushing all the geometry off until later? That's intentional. And then the horizontal component of the 410 Newton force has a negative X component. It's down below C, so it will cause, let's see, it'll cause clockwise rotation, and that's negative. So minus FABX multiplied by, what do you think, CBY? If you start to notice the pattern, you know this makes sense. X with Y, Y with X, so on and so forth. And that's it. Those are all the forces that can cause a moment about C. Now you might look at this and say, okay, I see what you're doing. You can probably get at all of this geometry, all those lengths. That's just geometry. We can do that. Don't know how we're going to do it yet, but we can do it. FABX and FABY, that was given. You draw a triangle, sure. But don't you still have two unknowns, PX and PY? Do we? Couldn't we say that the force P is also broken up predictably like this, and therefore there's a relationship between Px and Py? Those two vectors added together have to end up in the direction of 60 degrees down from horizontal. So how do I write that mathematically? Well, it's not too bad. Px, let's see, under Py be equal to what? Tan of 60. Correct? This is just a triangle. You can say, yeah, but isn't Py negative, so don't you need a negative sign? I'm not really thinking about that. I'm thinking of the triangle this way. There's P, there's Py, there's Px. Coming off of the horizontal axis that we're all used to doing, 60 degrees, that's what we want. And you can see my 60-degree angle is pretty poor. It should be more like this. That's more like a 30-degree angle, but oh well. So there's a relationship between Px and Py. So I have one equation, well, two equations, two unknowns, and I can solve it. Well, once I get all this geometry information, let's figure out the geometry. So if we've got, let's see, BC over here. I don't have a blue marker. Okay, that's all right. So we have BC over here. Here's BC, or what did I call it, CB? Here's CBX, and over here, this distance, is what I called CBY. So let's just extract the geometry and play with it. 100 millimeters with what, a 20-degree angle? Well, this side is just the sine side, so sine 20 degrees times 100. This side is just 100 times cosine of 20 degrees. And that's what CBX and CBY would be equal to. So somebody tell me what these numbers are, please. What is-
34.20,
Which one?
the sine 20.
Sine 20, the vertical side is 34.20?
Mm-hmm.
Okay. 34.20. These are all millimeters. We'll have millimeters times newtons, so no point in writing them down. How about CBX? Someone else. 100 times cosine of 20 is how much? Most of it?
93.969.
93.969, thank you. I guess we'll have to figure out CDX and CDY as well, won't we? That should be similar, literally. Because it's along the same line, right? So how much are CDX and CDY? Somebody else that hasn't answered yet.
CDY is 59.853.
Okay, CDX, someone else? It's the sheeting you put on the side of houses, CDX. $164.446, thank you. Okay, so there's the geometry, that's out of the way. What about FABY and X? How will I deal with that? Well, it's easy, we've already got the triangle here, right? In fact, FABY is nothing more than FAB, the 410 Newton force, multiplied by 200 over 2 over 205. So, if you say, well, should that be positive or negative, don't think that way. We've already taken the sign into account. All right, the sign is associated with the moment that the force causes. We've already figured that out from intuition, just by saying that we want a counterclockwise rotation to be positive. FABX, on the other hand, is just FAB multiplied by what? It's the other one,
Yeah.
45 over 205.
Yep.
And then, if we don't want to have px and py in the equation as unknowns, why don't we just do this and say py is px tan 60 degrees. So, we'll take py and replace it with px tan 60 degrees. Okay? Looks like a mess, but actually we're just about done. So from here, we've got, let's see, let me take all the px terms to the other side. Notice they're both negative, that'll make them positive. So px, with this term on the other side, times cdy, 59.853, plus py, but that's px tan 60 degrees, times cdx, 164.446, equals everything else. So FAB, which is 410, notice FAB multiplies both of these terms. I'm going to factor it out. I hope this is not terribly confusing. I'm factoring it out of both of these terms. So what I'll be left with is 200 over 205 times 93.969 minus, I factored out the FAB, 45 over 205 times 34.20. That's no better, is it? So to solve for px, all I have to do is factor out all of the common, or well, take out all the factors, pull px out, and then divide out by that factor. So px will be 410 times 200 over 205 times 93.969 less 45 over 205 times 34.20, all divided by 59.853 plus, I'm going to write this one first, 164.446 tan 60 degrees. Okay? So all I did was factor out all of the, well, really I factored out px, and then took what was multiplying px and moved it to the denominator of the other side. I just divided through by it. Okay? So take your calculators and see what you get. By the way, this is 200, not 20 degrees. The only degrees in here are 60 degrees right there. Okay? I'll grab the calculator and do it at the same time. Let's see if we come up to the same place. In fact, the calculator I think I'll use will be Excel. Maybe it'll be a little bit easier. There are the blue pins I was looking for. Let's see, let's just put it all in once. 2 times a quantity divided by another quantity. If you're watching and not bothering to compute this on your calculator, I'll show you how I use Excel. I'm going to set it up as 410 times a quantity divided by another quantity, and then I'll fill in those quantities later. Helps keep parentheses straight. So the denominator parentheses have 59.853 plus 164.446 times the tangent of a quantity. Now we've got to be careful. One thing you may not know about Excel is it expects to get angles in radians, not degrees. So if you put 60 degrees in here, you won't get the right result. However, there's another function, awful handy, that is degrees, or DEG, of an angle. Actually, it's radians, RAD, not degrees. So- Actually, maybe it's radians.
Haven't done it yet.
So it'll take 60 degrees, give me radians out of it. That takes care of my denominator. It sounds like a couple of you have finished with your calculator. And then I'm gonna put in the numerator, 200 over 205
Look at that.
times 93.969 less 45 over 205 times 34.20. My eyes are not so good, I just refuse to get glasses.
That's what.
Yeah, that's what we just
It's
got.
100.12? Okay. So PX is 100.1202. I'll just keep computing numbers in Excel, because the next thing to do is to figure out PY. In other words, we have to take PX times tan of 60, and that'll give us PY. I'm just gonna make a note that this is PX.
173.41.
Thank you. Then we need the square root of the sum of the squares from that to get the total magnitude of P. Okay, so when I took the tangent of 60 times px to get py, I got, does that make sense? Yeah, that makes sense. 173.41 or so newtons. And then when I said p is equal to the square root of px squared plus py squared in Excel, I got 200.24 or so newtons. And that was one of the questions, was how much force P had to be applied to get 410 newtons in AB.
So the answer is 200.24 newtons.
Yes. That's what I got. I want to go through my sum of moments again, just to make sure I got it all right. PX is that way, that causes a negative moment about C. I like that one. PY causes a negative moment about C. I went through it quickly and I'm questioning myself. AB in the Y direction causes, yes, a positive moment. AB in the horizontal direction causes a negative moment. So yeah, I'm okay with the signs, so it should be all right. All right, so those are the forces. What about the reactions, CX and CY? I can't calculate them yet. Why not? Well, because I haven't drawn them on the free body diagram, right? There must be some CY and CX. How do you think I should go about calculating CX and CY? I've already used a sum of moments on one of the members. Now I should probably sum forces, right? Now, that shouldn't be too bad, but I think I'm going to get rid of this figure because I don't think I need it anymore. I've written down the value of P over there, so let me put a box around it since that's one of our answers. And let me work on solving for CX and CY. If I sum forces in the horizontal direction, I'll have CX. Notice then FABX is negative and PX is positive. That sum of forces should come out to 0. So in other words, CX is equal to FABX minus PX. We'll figure out what that all is later. Summing forces in the vertical direction, I want to set up the statics first. We'll have CY minus FABY. It looks like minus PY as well. Therefore, CY is the sum of FABY plus PY. Let's see. Getting FABY and FABX is pretty easy. I've already got them written down over there. So we'll just substitute. FABY would be FAB times 200 over 205. I just copied it from right here. Okay. And PY we've already calculated as well. That's just a number now. PY is 173.41. It's right here. Of course, FAB is itself 410 newtons, and this is 173.41 newtons. To get CX, I'll take FABX, but that's just FAB multiplied by, it looks like 45 over 205. Minus PX, and PX is somewhere, oh, it's on my spreadsheet. It's 100.12 or so. And FAB is still 410. So this should give me CX and CY. If you guys have it, I'll just write it down, otherwise I'll go over to the spreadsheet and calculate it myself. Either way is okay. All right, let's see.
Negative 10.12.
That's about what would be in there.
Which one?
That's for the.
Must be this one?
The X, yeah.
So negative what?
10.12.
Okay. Anyone else have CY? Expect it to be fairly large.
573.41,
472.41 newtons.
or 573.41.
573.41, sorry. Thank you. So in other words, CX is actually in the other direction. Now let's think back to the original problem. Would these loads be reasonable for the original mechanism? Sure, it's a hydraulic cylinder. You really don't want to put a lot of sideways force on the cylinder. That's what CX represents, right? You prefer not to, because that's just not the kind of load it's designed to support. It's designed to support this load. So this is a good load for the cylinder. In fact, you can see that that's what should be expected, because had I drawn this with a closer to 60-degree angle, something more like that, you can see that generally most of the load, the external load applied about C, is mainly vertical load, right? And so it's not really a surprise that it takes a lot of vertical load to support it. There's very little horizontal load, and the horizontal load kind of fights itself in a sense. Right? One's pulling one way, the other's pulling the other, so the cylinder doesn't have to pull sideways very much at all to support it. Okay? Any questions about this problem?